I saw this question posted on Twitter, and it said it was from AAPT, but I couldn't find where it was from. But it was such an interesting problem, and I haven't solved it, but I want to solve it. So let me describe the problem, and then I'm going to try to solve it, and let's just see what happens. So the idea is I have a block on a frictionless plane sliding down, and the angle can change, but this distance from here to there does not change. And so the question is, what angle minimizes the time to get to the bottom? Okay, so let's just think of the extreme cases right away. So if I have a very, very low angle like this, then this block is going to have to travel a distance, almost distance L to get down there, but the acceleration is going to be very small because it's very flat. What if I went to the extreme case of a very, very, I'm going to draw it like this, a very high angle, then it would have a very large acceleration. But since this distance is constant, it's going to have to travel a much further distance. And so the question is, I mean, it seems possible that at some point, then it should be a minimum distance, because these two have very minimum times. These two have very large times. Okay, so let's just do the problem generically. I don't know what I'm doing. Like I said, I'm just going to start from scratch. So let's draw a force diagram. I have the downward gravitational force, the normal force, and that's it. And then so let's call this the x direction, which seems kind of weird, but it's fine because we're going to get the acceleration in the x direction, and even though that depends on theta, it's fine. So there's only one force that causes the block to accelerate, and that's the component of the gravitational force right there. So I can write in the x direction, F net x equals mg, right, that's the gravitational force, times the sine of theta. And then let's just check real quick. So if theta is 0, then the acceleration is 0, right? If this is a flat plane, the acceleration is 0. If it's 90 degrees, the acceleration would be mg, the net force would be mg. And this is going to be max. So we get the acceleration as a function of x. So ax is going to be just g sine theta. So now I want to find the time it takes to get from here to there. So I can use, let's go ahead and just use the kinematic equation. I'm going to say, let's call that x equals 0. X equals x0 plus vx0t plus 1/2, that's a t, 1/2 g sine theta t squared. Now if I call that x is 0, then x0 equals 0, vx0 equals 0, so I get x, the final x, is going to be equal to 1/2 g sine theta t squared. Now I want to find the time. So let's just go ahead and solve this for time. T squared is going to be 2x over g sine theta. So t is the square root of 2x over g sine theta. But that's not the whole problem, right? Because x also depends on theta. So let's just draw this in another picture. I ran out of paper. So let me draw a picture to get the value of x. So let's see, so far I have, this is important. I have t equals the square root of 2x over g sine theta. That's my time. But here is my block. This is L, this is theta, and this is x. So if I take the cosine of theta, that's going to be adjacent over hypotenuse, that's L over x. So x is going to be equal to L over cosine theta. Right, if I just solve that. So now if I plug that in, I get t equals the square root of 2L over g cosine theta sine theta. Okay, that's my time. And I want to find out the minimum time. So in this case, if I want to find the minimum time, I'd do a max-min problem. And I don't want to do this because this does not look nice. So let's take the derivative of time with respect to theta. That seems really weird, okay? But that's what that is. And we're going to set that equal to 0. Because imagine this. So suppose the time, here's theta and here's time. I know that if theta is equal to 0, I get an infinite time. If theta is equal to pi over 2, I get an infinite time, right? And which we can see right here. If I put in 0, I get 0 on the bottom because of sine. If I put in pi over 2, I get 0 because of cosine. So it should do something like this, I would think. And we're trying to find the minimum time is where the slope of this line, the slope of that function is 0. So we're going to find the slope, we're going to take the derivative and set it equal to 0 and solve for that theta. I think this will work. Shouldn't be too bad. Okay, so I'm going to rewrite this as t equals, I'm going to pull all this stuff out front, square root of 2L over G, because I don't care about that. This is a constant. Times, let's write this as cosine theta sine theta to the negative 1/2. I like working with it that way better. And I'm going to call this K, okay, because I don't really care about it. So now I'm going to say dt d theta equals K, and then I have a power rule, right? So if I bring this down front, I get negative 1/2, and then I have cosine theta, sine theta, and I need to decrease this by 1, so I get negative 3/2, right? When you take the derivative, you decrease the power by that. But now I need to take the derivative of the inside, so because of the chain rule. So the derivative of cosine theta sine theta, I have to use a product rule. So the derivative of cosine theta with respect to theta is going to be negative sine theta times sine theta plus cosine theta times the derivative of sine theta, which is cosine theta. That looks nice. Oh, not quite. Okay, so now let's just simplify. I get negative k over 2. This is going to be negative sine squared. That's just a shame. Negative sine squared theta plus cosine squared theta. All of that over cosine theta sine theta to the 3/2. And I want to set that equal to 0. So now I want to solve for theta. Okay. Gosh. Solve for theta. There's probably a trick up here. A trig trick. Okay. Let's go ahead and solve this by plotting. Let's plot, we'll call this dt d theta, I guess. Let's call it slope as a function of theta. I'm going to plot this as a function of theta from 0 to pi over 2 and see what I can see if it does cross through the origin, because I know that it simplifies, but I don't want to simplify it. And I like Python, so, and no one can stop me. And then I'm going to plot this function and see if that agrees with that. So let's jump over. Now, one of the things when I plot this, I'm going to need a value for k, and so k depends on these values on L. So let's pick L as a meter. That's all I need. Okay, and G is 9.8. So I'm switching over here to Python. I already got this set up because I knew that I might have this problem. So we're going to make a graph. G1 equals graph. X title equals, I'm changing theta. It's theta in radians. I would just leave it off. And then the Y title is going to be equal to, let's just say slope. And then I'm going to give width equals 400, height equals 200, just because otherwise it doesn't show very well. F slope, let's just call it F1. F1 equals G curve, color equals color.blue. And now what I'm going to do is say theta equals I don't want to do 0 because the slope would be infinite at 0 according to what I look over here. So let's say 0.05. Okay. And then d theta is 0.001. That may be too big, but that's fine. And now I can say while theta is less than 0.9 times pi over 2. Again, I don't want to go all the way to pi over 2 because I think it'll go and be infinite. The first thing I'm going to do is to calculate the slope. So slope equals, I'm looking at my equation right here. Oh, I need this k. So L equals 1. K equals square root of 2 times L divided by G. So the slope is going to be k, negative k over 2 times negative sine squared, negative sine theta squared plus cosine theta squared. All of that divided by cosine theta times sine theta raised to the 3/2. So now I'm going to plot that. F1 dot plot theta slope. And now I'm going to increase theta. Theta equals theta plus d theta. I'm scared. Let's run it. Aha, something happened. Can't find variable g. Okay, that's not a bad error, right? Let's save this as APT problem. That's not what I said. I don't really care. Okay, just want to save it. So I never defined g. So let's define g right here. G equals 9.8. Run it. Okay, well, it worked. Okay, and so you can see right here, I get, I'm going to change this from 0.55 to 0.8. So I'm going to say 0.55, and this is going to be 0.8. That would just zoom in on that graph. And there you can see that, ooh, I missed it. So let's go from 0.7 to 0.9. So remember, I'm starting, and there. So there's my intercept is right there. So that, right around there, I could zoom in if I wanted to, but I think this is going to be good. 0.784 looks pretty good. Okay, let's make another graph, and let's plot the time as a function of theta. And let's see if that is indeed the minimum. So G2 equals graph, x title equals time in seconds. No, x title is going to be theta. Y title equals t in seconds. And then width equals 400. Height equals 200. F2 equals G curve. Color equals color.red. And I'm going to again, let's do this from 0.5 to 1 point to 0.9. That's fine. And now I'm going to plot the other thing. So I need to calculate that. So this is going to be time equals, I'm going to use my equation. I'm looking at my equation right here. It's the k, let's just write this, square root of 2 times L divided by cosine theta times sine theta. And now I'm going to plot that. It looks like too many parentheses, but I think it's okay. And then I'm going to F2 dot plot theta t. Okay, let's run that one. So now I get the two graphs. Here you can see the minimum is around the same value, right? So that does look good. Somewhere around, it's kind of hard to tell. So this says theta is 0.784, somewhere around there. And this has, they're not the same, they are the same scale. 0 is right here. So they agree. Okay, so I'm not really good at solving algebraic equations with trig, but I'm good with Python, and so that's that. So I will include this link to this code. If you want to play with this code, you can. It's down below. I'm really kind of pleased with those graphs. They look pretty cool. So maximum problem is pretty fun. I didn't really like the algebra at the end, but that's that. Okay.